Okay. So again, this class it's called hydrology or engineering hydrology, but nowadays I think a more appropriate name is water resources engineering. Of course, we're going to end up describing or defining what water resources are and all that stuff, but for now, I'll just let you know that the field of water resources engineering is divided more or less into two sub areas, right? Hydrology and hydraulics. Hydrology, by the way, I don't like to write text so much, so if I'm not writing equations, I'm probably not going to write it all, so you can take your notes. Hydrology is the study of the water cycle. Water, when it rains, what happens? Does it infiltrate? Does it run off? When it gets to the rivers, what happens there? Does it evaporate? Does it travel to the ocean? All that stuff, all that study of the water cycle is called hydrology. Hydraulics, on the other hand, is the study of how, well, it's the study of applying fluid mechanics to a hydrologic process. In other words, water in a river, how deep will that river be? Water crossing under the bridge, is it going to flood the bridge or is it going to be pressurized underneath? Water in a storm sewer system, what's the velocity, what's the flow rate, what are all these different properties? So hydraulics is essentially an application of fluid mechanics into hydrology. And hydrology itself is more of a science than it is an engineering field. It's more of the study of the water cycle. You've heard of the water cycle before, right? I think we've all had 4th grade science at some point. So can anybody explain what the water cycle is? Give me the steps. Yeah?
I mean, it rains, and then the rain runs off to either like a lake or the ocean or whatever, and then that evaporates, and it just starts all back over.
I like that. I like it. What's your name?
Caleb.
Caleb what?
Caleb Pollard.
Caleb Taylor Pollard.
Caleb Pollard.
Taylor Pollard. Yeah. Awesome. I'll try to remember that. Anyway, so according to our friend, water rains, right? And rainfall is essentially just precipitation. It's a precipitation event where the clouds, and clouds are combinations of clouds are aerosols basically. So it's water vapor with suspended solids and suspended liquid droplets. When those droplets become heavy enough that the water vapor cannot hold them, then rainfall occurs. They fall down in the form of raindrops. Of course, that ends up, let me get a better pen. That's fine. Rainfall ends up landing on the ground, and from there it travels up. You said a word. You didn't say travel. You said something else.
Runs off.
Runs off. Good. So this rainfall becomes runoff. And from there, it's going to reach either a lake or an ocean or some other water body. And then that water body will evaporate. And that evaporation will once again become a cloud. Is that all there is to the water cycle?
And then condensation.
There's other, yeah, exactly. There's other processes occurring. This is like the most basic form: rainfall, runoff, evaporation. But there's other processes. So let's talk a little bit about rainfall. Is rainfall the only form of precipitation? So is rainfall the only way water can come from the skies to the earth? No? What other forms are there?
No.
Snow, hail, and then
Sleep.
sleet, good. Yeah, there's all these different ways. And pretty much in every single process, we do have water, H2O, coming down into the ground, but in different forms. So rainfall is water coming in as water in its liquid form. We do have snowfall, which is a crystalline form, which is not really technically ice, right? It's more of a nice little crystal. And of course we have hail, which is ice, actually ice. And we have all these other different processes. So I'm going to try not to use the word rain here or rainfall because yes, rainfall is the most common form of precipitation, but it's not really the only form of precipitation. So instead, I'm just going to use the general blanket term, precipitation. This is a new pen. You see, it still has a lot of ink. It doesn't work very well for me. So I'm going to use the blanket term, precipitation. Okay. So precipitation is the process through which, water from the clouds becomes water, lands to the ground. Awesome. In the ground, water runs up. Is that the only thing that can happen to water? Run up?
Penetrates into.
It can also infiltrate into the ground. Good. So in addition to runoff, we have what's called infiltration. Good. So water falls on the ground. Some of it is going to get infiltrated. Think of it as absorbed by the ground. And whatever can't be absorbed is just going to continue its path. Maybe it's going to run off, and as it runs off, become infiltrated. Maybe there's no room for it in the ground because of the moisture levels, and it'll just continue moving until it reaches a water body. Now, water that is infiltrated, it doesn't just stay there, right? It travels, and the way or the form in which infiltrated water travels is what we call groundwater flow. Excuse my bad handwriting, but it's the only handwriting I have. So it's groundwater flow, okay? Now, what can happen to water that's underground? Well, it can flow, and at some point, it's going to reach a water body. So it's going to eventually exfiltrate into a water body. Or what else can happen to water underground? Yeah, it can keep traveling until it reaches a water body. Anything else?
What about getting absorbed by plants?
Exactly, right? It can get absorbed by plants, which means that if we do have plants, obviously I'm oversimplifying here, but if we do have plants, they will absorb some of the groundwater. They will consume, I think is the correct word, consume some of the groundwater. Plants that consume water release that water through a process called evapotranspiration. I guess I'll write it here. Evapotranspiration. Good. And that evapotranspiration can then go back to become clouds. Typically, water in water bodies just evaporates, but even within water bodies, water can also infiltrate. However, large water bodies such as lakes are typically saturated, which means that their ground has already infiltrated as much water as it can. So normally for water bodies, evaporation is really the only form of loss of water because the ground should already be saturated if they're large water bodies. Good. There's still other forms of water processes going on, but I think those are the most common ones. Those are the ones that I would like to work with in this class: precipitation, infiltration, groundwater flow, runoff, evapotranspiration, and evaporation. Hydrology, of course, is the science that studies this cycle. We call it the water cycle, but if you want a more official or technical term, we could call it the hydrologic cycle. And studying it is actually going to be part of this course. Okay? We can measure rainfall, but just because we know how much it rains doesn't mean that we know how much it's going to infiltrate, how much it's going to run off. Also, just because we know how much infiltration there's going to be in one area doesn't mean that we know how much infiltration there's going to be in another area. There's a lot that we need to understand. There's a lot of this that we need to understand before we kind of go out there and just say, well, we are hydrologists or we know hydrology. Okay? Now, all that will come in time. This is the first day of class, and I do want to cover some of the kind of like base terms or base concepts. Okay? When we talk about water resources, we typically refer to these as those resources that we can develop or use to control water. I'll just give you one example. It rains. Maybe we're dealing with asphalt where there's no infiltration going on. So a lot of what it rains just runs off. What happens if there's too much asphalt, right, and a lot of rain? Pond up. It's going to pond up. It's going to flood, basically, right? And sometimes we don't want that. So sometimes we can have an overabundance of water. Water resources would consist of controlling that runoff. We can control it through a storm sewer system. We can control it through a detention pond. Or we can control it through pre-construction methods, such as not adding that much asphalt. Right? So there's different ways that we can control these water resources. But stormwater is not really the only water resource that we have. Can you think of any other way that you can use water other than play around when it rains? What do we need water for? Drinking, good. Drinking water is a very important water resource. Drinking water, which we call water supply, is one other important water resource. Can you just get this glass and just stick it outside, collect some rain, and drink it and survive that way? Not really, right? So that means that drinking water, what we need, is actually not really what the environment provides, at least not in its natural form. Which means that we are going to have to focus not just on the quantity of water, not just on how much water we have, but also on the quality of water, right? What is the chemistry going on inside the water so that we can actually drink it? We drink water. What else do we do with water? Release it, right? Through a process called?
Urinating.
Urinating, good. Yes. That makes you feel uncomfortable, let's just call it pee-pee or something, I don't know. We can also release it through another process called?
Sweat?
Diarrhea, yes, correct. Oh, sweat, actually, sweat would have been better. So, we release water. Now, I'm going to focus on the toilet releases because those are easier to control. I mean, sweat just like evaporates eventually. And we can't really say, oh, I flooded my house because I sweat too much. Oh. Anyway, we're going to look at toilet releases. That water, which we call wastewater, has to go somewhere. Back in the old days, what did we do? We just said, well, it's water. Let's just throw it out there. Great. And then we had all these different sicknesses and pandemics and all that crap. So now we realize that we don't just care about water quality when we're drinking it. We also have to care about water quality when we're releasing it back into the environment. Okay, so water quality plays an important role in the water we drink and the water that we release. Okay? We control these water resources in terms of where they are, how much is released, how much is produced or brought into, and even how they travel. Sometimes we do this process called routing, which means you have this much water, it's too much for my parking lot drainage to handle, so I just make a really, really long system so the water spends a lot of time traveling so that by the time it gets to the end of the system, exactly. It would have been a smaller or lower rate. Good. So we control it, essentially. Now, there's a lot of science involved in hydrology, and we are going to deal with that science in this class. So like I said, a lot of equations, a lot of meteorology, a lot of chemistry, and some fluid mechanics as well. But before we get into the science, I think it's important for us to understand water demand and supply. Because I think we can't really function in a vacuum. I can't just throw equations at you and say, use them. I want you to know how you're using them and why you're using them. So I want us to think of water resources in terms of demand, how much water we need, and supply, how much water we can provide or how much water we have. Okay? Water supply can be natural or it can be engineered. Okay? Natural water supply, rainfall, rivers, lakes, or natural lakes. There's not that many in Georgia, but lakes. And then engineered water supply would be stuff like the water distribution system that brings water to your tap, brings you tap water, essentially. So there's engineered and natural systems, and obviously for the most part here, we tend to use engineered systems, right? Nobody, I'm assuming that you don't just go into the forest and just like take a dump there and be like, okay, let nature take care of it, right? I hope that you use some structure that carries that water into a treatment plant before releasing it into the environment. So we typically take advantage of more engineered systems, but we also use natural systems. Can you think of a natural water system that we, maybe not everyone, but that we may use? Just think. Well water, but we need to actually put the wells in. So that's still engineered. Any other, think natural system, think something that there's no machinery needed. I am from Puerto Rico.
Ocean?
Beaches, right? Yeah, that's an example of a natural system where we actually don't need engineered materials to actually take advantage of it. And we don't really drink seawater, but we enjoy it, so we use it for recreation. It may not seem too crucial or important, but even recreation is a way of using water. So we typically consider it as well. It may not be as important as drinking to survive, but it's still important as well. there are several problems that we as water resources engineers are going to have to address. Problem number one, we have a lot of water demand, not enough supply. Is anybody here from California? There we go. So California has a crappy, terrible water supply system. Where does your water come from?
I'm from Sacramento, so I'm swimming the Sacramento River.
Colorado, actually. Yep. California has terrible, terrible, terrible water resources, so they bring their supply from Colorado and Nevada, okay? Because they just don't have drinkable water. And that's one problem that water resources have to address. Then we have the flip side. We have a lot of water supply, but we don't actually need that much, so we need to figure out what to do with it. And you may think, well, how is that a problem? Well, it is a problem. Think of flooding, for example. We can try to come up with systems to capture rainwater and maybe use that to treat it to produce water supply, but that actually doesn't happen. Nobody really takes rainwater directly from the sky and then convert it into water supply. We actually wait until it gets to the rivers. There's many reasons for that. One such reason is that we don't have the ability to actually treat it or treat that much rainwater in order to have the quality we need. We actually need the rainwater to travel through the rivers first, so because that's natural treatment, before we can actually take it and then treat it and then use it. So we have those two problems: too much demand, not enough supply; too much supply, not enough demand. And we need to address both. And that's the thing. With water resources, we need to know how to address both problems. Now this week, I would like to study water demand, just because we're not going to cover it in the later section. So this week, I want to study water demand, so that in the future weeks, when we study how to handle water supply, we know what it is we're trying to handle, right? And why we're trying to handle it, okay? We've already talked a little bit about natural sources of water supply, and I gave some examples of engineered sources of water supply. Again, your toilets, I guess it can be water supply. Your toilets, your treatment plants, and your stormwater conveyance system. We said that we need water to drink. We said that we need water for recreation. Is there any other reason why we may need water? Yes? Cleaning, yeah, cleaning, good. Hygiene.
Put out fires.
Put out fires, firefighting, good. We need water for firefighting.
Irrigation.
Irrigation, good. We need water for our crops. So,
Power.
sorry?
Power.
Hydropower, that's correct. We need water for power. So we need water for a number of reasons, not just to drink and survive. Now here's a problem. In most cases where we do need a lot of water and we don't have that much, we may not be able to supply water for all of these things. So we're going to have to, unfortunately, start a practice of prioritizing. I have this much water. I need this much to drink. I also need this much for my water park. Which one do you think is going to take the priority?
The water park.
Did somebody say water park? Jesus Christ. All right, well, let's just say we need to prioritize things, okay? How we prioritize, I guess it's up to you, but sometimes, right, we need to realize that we won't have enough water to supply to all of our needs. And that happens all the time. For example, there are places, and like California, I'm using California as an example because I hate California, but nothing against you or your state. But in California, during drought seasons, they do have some regulations that say, well, you can only use water on certain days for outside usage, right? Like washing your cars and pressure washing your driveways. In Puerto Rico, it gets even worse. In Puerto Rico, when we have a storm, the storm decimates our infrastructure, which happened in 2017 and happened again a little bit later, a little bit more recently. And what we do there is, well, we're in drought, we don't have enough water, we don't have enough electricity to supply, so they actually give us water like every other day, or 2 days in, 1 day out, or 1 day in, 2 days out. So we need to regulate our water, and then we cannot really use that water for things other than drinking and hygiene, personal hygiene, not car hygiene. So you can use water to drink, you can use water to take a shower. You're not allowed to use water to wash your dog, which is really funny. It's like, how are they going to check that, right? But you can't really clean your dog, give your dog a shower, you can't wash your cars, and you can't pressure wash your driveways or wash your houses. In my house, my dad's a water resource engineer, so obviously every time there's a storm coming, we do have a cistern in the house, or I guess in my parents' house, they do have a cistern, so every time there's a storm coming, it's like we just fill up all the cisterns, right? Because we know that there's going to be some problems with the water supply, and we want to make sure we have our own water. In Bolivia, where my dad's from, when the wells dry up, we don't really get that much rain over there, but when the wells do dry up, then essentially water is reserved only for drinking, not even for hygiene, right? Because there is no water, there isn't enough water. So it gets to a point where you have to choose, do I want to smell good or do I want to live? And for the most part, people just live, right? They drink water. But essentially, you get to a point where water is only for drinking, not even for showers or anything else, because the wells dry up. We don't really get that much rainwater. We don't have water. So we do have those problems. Those are real problems. We may not seem to experience them here, but there's a reason why we don't experience those problems at that scale here. Because water resources engineers, because they're already taking care of all that stuff. Bolivia has lakes. They're drying up, but they have other lakes. But of course, they don't have the infrastructure to bring water from the lakes to the populations that actually need them. So obviously, you can see why this is a very passionate topic for me, not just because I make a lot of money from it, but because I like, right, that this is actually stuff that actually helps communities such as my own, right? And such as your own as well, as you will see when we start to look into the intricacies of water supply and water collection systems. Okay? I'm going to define some terms here. You don't have to memorize these terms. I just want to make sure that when I say stuff, you know what I'm talking about, right? So we say that withdrawal consists of anything that diverts water from its source. For example, for irrigation, typically we collect water and then we move it, right, from where it lands. Let's say water lands on a certain patch of land, we collect it, or from a river, we move it and then we use it to water our crops. For recreation, for tap water as well, we collect water from a lake, from a source, and then we move it to your homes. Even if you did want to try to collect your own stormwater, which I think it's awesome, right? There's obviously some political issues there, but even if you did try to collect your own stormwater for your own use, you'll find that you actually won't be able to collect enough or collect what you need, because most water ends up in the rivers and the lakes. Your watershed, so the area that receives rain, which is your land, unless it's a very big area, it's not going to be that very big, and you're going to be limited to how much you can collect. And on top of that, it's not going to be treated. So even if you did want to collect your own rainwater for use, you'll find that you won't have enough. And that's why it's necessary for us to practice withdrawal, where we take water from one source, move it into another source. So we take it from where there is and move it to where there is need. Parentheses. I thought about, you know how these, how governments all suck, and when you install like solar plates in your house, then they want to tax that because you're not using the electricity or something like that. I guess you're not adults, but if you install solar plates in your house, you'll be like, oh my God, I'm saving so much money. And then the government will be like, oh my God, you're saving so much money. Give me some of that. And then you'll tax. So Puerto Rico, for example, because of our power grid is really bad, there's a big movement to install solar grids in people's houses. And now they're being taxed at such a rate that you're paying more for the solar power than you are for actual electricity. You pay more in taxes than you are for an actual electric service. It's really crazy, right? Same thing happens with water. If you somehow start to collect water, and let's say you are surviving, you won't, but let's say that you are surviving, and then you decide to disconnect from the tap water system, you are going to get taxed on that. There are reasons for that. California, for example, is one state that has collecting stormwater criminalized. It's actually criminalized. It's not just like, hey, don't do it. It's like, you cannot do it, right? I hate that state so much. They have all these laws that just don't make sense. Now, here's the thing. If I didn't know better, I would think, oh my God, this is crazy. They suck, whatever. And it's true, but there's actually a little bit more to that, okay? It's not just because we don't want you collecting water. It's because rainwater, right, after you use it, it needs to be treated. And before you use it, it needs to be treated. And that treatment needs to happen. Now, here's the thing. It's actually more expensive for all of us to try to treat our own water than it is for us to actually throw our water to a common treatment supply, right? Because treatment works better in large quantities. It just works much better. And sometimes treatment needs large quantities in order to occur. There are some treatment procedures that use certain bacteria and use certain microbes, and those microbes can only exist under large surface areas. So if you have a small area, they will not live, they will not grow, and you won't be able to treat your water. So I know that sometimes a lot of these rules don't make sense, but there is some hidden or hidden reasoning behind them. I don't agree with the whole taxing and stuff like that, but at least when it comes to the water treatment and the environmental impacts, I kind of do agree there. In the fact that we do need to think not just in terms of, well, I have my own water, what do I do with it? We got to think in terms of what's the best way to treat all this water or to supply all this water and so on and so forth. Okay? We have other uses of water that don't require us to withdraw them from their source, and those are called non-withdrawal uses or non-withdrawal sources. Sometimes we don't actually need to move water from its source in order to use it. We mentioned drinking, and we mentioned recreation, we mentioned irrigation, we mentioned hygiene, we mentioned cleaning. There is one other use of water that we haven't mentioned. Can you think about what it is? And it basically, that doesn't mean, we don't need to take water out of its source to use it. I'm from Puerto Rico. Storage? I mean, but we store it for something, right?
Transportation.
Sorry?
Transportation.
Transportation, good, right? I keep saying I'm from Puerto Rico, but I hope you understand why. It's like, you know, we have to get there somehow. Like the Spanish people have to get there somehow. Transportation, we use water for transportation. Non-withdrawal uses of water mean that we don't have to move water in order to use them. And transportation is one of those non-withdrawal uses. So navigation, and of course, sometimes recreation when we're talking about beaches. Good, 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 good. This class ends at 1:45, right?
Yeah.
Okay, Josh, you're gonna be my timekeeper. Let me know when it's 1:44 so I don't go over time, okay? All right? If you don't, you're not just failing me, you're failing your classmates. All right. Within our uses of water, we have withdrawal, we have non-withdrawal, and we also have something called consumption. Now, my friend over there, what was your name? Whoever said the plants thing? Sorry?
Bethany.
Bethany?
Bethany.
So Bethany mentioned one source of consumption, right? Plants, crops. There are other sources of consumption. Now, here's the thing. When we say consumption, we essentially mean water that we use and that is no longer available. Now, drinking is interesting because it is a form of consumption, but we actually do release most of it back, right? So it's kind of consumption, but also not really consumption. We typically round it, lump it with the consumption uses, but typically consumption refers to water that is no longer available. So plants, they consume water. They don't release that water back into our water resources systems. They release it into the atmosphere through evapotranspiration. Some of the water that we drink, we release it through sweat. Again, transpiration, right? So typically consumption is water that will not go back into our water resources system. Instead, it just goes back to the sky, basically. So we need to wait for another cycle in order to get it back. Okay? When we say water supply, I know I talked about supply and demand. Typically, when I say the specific phrase water supply, I mean the water that's going to come through your plumbing, water that you're going to drink, water that you're going to use from plumbing. I know that water supply can mean other things, such as, well, water from the lakes. That's supplied water as well. But from an engineering standpoint, when you talk to an engineer and you say water supply, the engineer will think of the actual system that brings the water into your house or into your building and whatever. This type of water supply, water that comes through your tap water system, is typically the one that has the highest priority among all applications. It has higher priority than navigation sometimes. It has higher priority than recreation, and it has higher priority than other sources. Okay? Water supply is interesting because it's not just about moving water, it's about controlling the quality of that water. Water supply typically requires good quality. Now, here in the States, it's a little bit interesting because we make sure that any water that you get should have a certain base minimum standard of quality so that you don't sue. But let's go back to the Virgin Islands. Anybody here from the Virgin Islands? Our neighbors? No? So my neighbors in St. Thomas, it's very, very close to Puerto Rico. They actually don't have that much water supply, and they don't have the infrastructure to treat all that water. So what they do instead is they have two different water supply systems. One that goes to the tap water that you're going to drink and use for hygiene, and one that goes to tap water that you're going to use for washing your cars, for flushing your toilets, and for other types of uses. So we actually have two separate supplies of water with two different sets of water quality because there just isn't the infrastructure to provide water quality for all of the water that is supplied. We don't really do that here that much, but essentially the idea is you want to determine, right, what the minimum standard is for your water supply. And of course, if you're drinking something, you typically need a little bit better quality than if you're just using it to flush toilets, right? I mean, you can flush toilets with anything, because it's all gonna go back to a treatment. I've always wondered, and this is just, again, a parenthesis, I always wondered if there's ever been like someone that has urinated enough to actually make the toilet flush itself. I don't think that happens, right? Because you need you need a lot of water. You need more water than what you can actually store in your bladder. But if you get like a large animal, like a gorilla, do you think that the toilet can self-flush? I think it can, right?
I think it'd be more impressive to get a gorilla to like use it.
That would be even more impressive, right?
Yeah.
Just the fact that that's happening. Now, Breno,
Yeah,
I don't recognize you with your hair like that.
yeah, we
I thought you had long hair, long dark
I
hair.
did, yeah, I cut it too.
Now you have short,
Yeah.
weird hair. That's all. Welcome, Breno. Good to have you in my class.
Thank you.
Yeah. I mean, back to the class. Typically, this type of water supply can be divided into 3 subcategories, right? We use water supply for municipal use, for industrial use, and for waste dilution use. Municipal just stands for anything that goes to or that is controlled by the government, right? Stuff like providing drinking water for the houses, which typically gets subcontracted through some companies, but who knows, sometimes the government provides it themselves. In Puerto Rico, all of our water, electricity, and trash is government controlled. I think electricity became private just a year ago or something. In Fulton County, for example, my water and sewer, I live in Fulton County in the north side of the county, my water and sewer is actually public, right? It's Fulton County water and sewer, right? But if you go to a different county, you may actually not have public water and sewer, you may have private water and sewer. So typically what happens is the counties or the municipalities, that's more general, they are going to determine whether or not they can handle or manage a water supply system. And if they can, then they will. But if they can't, then they will subcontract the company that can manage the infrastructure and the payments and all that stuff. Sometimes one entity can handle the infrastructure and one entity can handle the administration. For example, I live in a neighborhood in Alpharetta, which my wife and I moved in. We moved in shortly after getting married. Actually, the day after we got married, we moved to this new neighborhood. And this new neighborhood, it's pretty interesting. The water supply, it still comes from Fulton County, but we actually don't pay Fulton County. We pay this other company. And this other company, they manage all the meters and all that stuff. So it's like we're paying someone to tell us how much we need to pay. But it does happen. So the management of water resources is not just about one entity. It's typically a multi-entity thing, right? Where we have multiple entities just managing water resources. Okay. So I will say though, if you're just gonna like hang out and talk like those 2 guys in the corner, you don't have to do it in the classroom. You can go outside. You don't have to be in the classroom. Attendance is not necessary for this class, okay? Just a note for everyone. I don't want to call names, but those 2 in the corner over there, in that last corner, just everybody stir that way. Just look that way, everyone. There we go. Thank you. All right, thank you. Thank you, by the way. All right, so we can divide municipal water into domestic use, public use, commercial use. I really don't want to go into and just like give you a list of things because you can read those from the book. What I want you to understand is that typically this water will receive the highest priority. Because even though we use it for recreation, we use it for cleaning and for hygiene, we also use it for drinking. And because it's all the same system, it should receive the same priority as what our drinking water obtains or gets. It's very simple, not simple, it's typically, I guess we can say simple. It is simple to determine how much water we need, but normally we can't really determine that perfectly, so we typically want to go a little bit above that. Does anybody know the population of Marietta? Somebody look it up? Yes!
400,000, I think.
400 what?
No, yeah, 400,000.
400,000. Awesome. I forgive you, by the way.
No, it's 40,000.
Very good. 40,000.
I don't know.
Are you just messing with me? Or just like saying?
No, because I saw it once and it's around.
All right, let's just say.
Number 4.
Let's say 400,000.
Marietta is 60,000. 60,000.
All right. Be forgiven. All right. 60,000. 60,000 people live in Marietta. You are designing a water supply system for Marietta. Are you going to design for 60,000 people? Why not?
It grows every day.
It can grow, okay. Let's suppose that you're designing for Marietta and they have a cap on how many people can live there, and only 60,000 can live. Are you still gonna design for 60,000 people?
No.
Why not?
Because everyone's not gonna be using the water at the same time.
Not everyone's using the water at the same time, correct. Yes,
Also, if people who travel in and out, they don't live here.
exactly, right? I come here, I drink Marietta's water, I use Marietta's sewer system a lot, okay? But I don't live here, right? I'm from another place. So I'm not really part of that statistic, but you still have to design for me. In fact, I'm here during business hours, which is when most of this usage occurs. So, I'm kidding, by the way. It's not like I'm there all the time. But anyway, when we design water, we need to understand how much population we are designing for. And that is not as easy as just picking a number of how many people are here, how many people will live here a year from now. No, it's a little bit more complicated. You need to look at the industry conditions, right? We have schools here, so we have a lot of out-of-state students, which means that we'll have much more demand during school time and less demand during winter and summer. Okay. However, this is a commuter school as well, so even our school will have much more demand than what the actual number is, right? How many students are at KSU?
41,000.
41,000. Let's assume that only half of, no, more. Let's assume that 80% of them live in Marietta, but the other 20% do not live in Marietta. Most faculty actually don't live nearby. I live like 30, 45 minutes away, and I'm actually neighbors with several of my colleagues, so we don't live here, right? So we need to consider all that. Those are large, considerable numbers that are going to affect our supply and our demand. Okay? There's a nice little figure in the book that I want to show you. One thing I will give credit to the book is that the author has done a great job at putting together figures. And this figure kind of shows a little bit of the different dynamics between water systems. Essentially, we can obtain water from a lake or some other surface water source, or from wells, which is groundwater. And that water can be used for municipal use. We have household use, commercial use, small industries, and public uses and losses. When I say losses, this is just water that's lost to the system. Maybe leaks, maybe other deficiencies. Okay, so it's basically water that it's just lost, we're never gonna get it back. These percentages actually correspond to some average values. So it's average values for a city of 150,000 population, so they're not really, don't take those percentages and then apply them to every city. Okay. All that water that is used has to be treated, so we do have sewage treatment before it gets discharged back into the environment. Water can also be obtained and used for industrial purposes. Typically, industrial uses do not use well water for a lot of reasons. Well water is far more limited than surface water, so typically well water is reserved for this municipal use, which does have priority. And of course, industrial water has to be treated, and industrial treatment has to be a lot stronger than typical wastewater treatment, because a lot of the stuff that industries pump into your water are actually a little bit harder to treat than what we pump out of our bodies. Okay, so industrial treatment is a lot stronger. Yes?
Can you name some examples of what pumps out industrial waste?
So,
Is that like Amazon or?
yeah. Basically, warehouses, anything that uses water for production of materials. Okay, maybe Amazon not that much, but so industrial wastewater is actually a really nice field that I've done some projects in. Some of these industries involve textile industries. Okay, we have nuclear industries as well, nuclear power industries. We have basically anything that's not used for you to drink. That basically we need water, we need to mix it with something, and then we need to discard it eventually. Nuclear cooling, I think, is one of the best examples, right? Because we need water, we need to mix it in order to generate the cooling fluid. But once that cooling fluid has been used, depending on what combination you use, we don't reuse it, right? And then it needs to be discarded. So typically, industrial wastewater is really, really dependent on the industry that it is treated. So it's not like, if I design a wastewater treatment plant, I've done industrial wastewater treatment plants before, I can't just take that design and then use it for another project. It's very, very specific to the industry you're treating. Okay? I'll try to give more examples throughout the semester. Sometimes we use water, but we don't actually mix it with anything else, which means that it just comes in. Maybe we use it to extract temperature from it, so to cool, but not in nuclear cooling, but typically just normal cooling, standard cooling, where it's just water coming in through a pipe, and then a thermodynamic process just exchanging temperatures. And then we can just release it. We can just release the hot water. In those cases, we typically assign a value called waste dilution, which is essentially natural treatment. I mentioned earlier that you can't just get stormwater, treat it yourself, and drink it, because it needs to come up with some natural treatment first, and that's the natural treatment that occurs with the stormwater mixing in with the rest of the water, and the general flora and fauna of the environment just treating the water itself. Natural treatment, you may not realize it, but natural treatment is actually very, very, very crucial and important for our water supply. In fact, everything we do counts on natural treatment as well. We have a wastewater demand. So let's say we have, I'm going to draw this nice little diagram here. Here's me. I'm trying to cross my hands, but I guess you can't see. Water goes this way into a wastewater treatment plant. And this wastewater treatment plant is going to treat the water until its dissolved oxygen, its microbes, its biota is down to a certain percentage. I'm just going to throw numbers out there. It's not that simple, but let me throw that numbers out. Let's say that we want to treat water such that the biota in it is down to 5% of the water. So it starts with like maybe 80%. We want to treat it down to 5%. Then we release it back into the environment, a lake or a river. Let's say a river. It's most likely a river. But then we also capture water from this river. We treat it as well. We filter it and we treat it, and then it goes back into my water supply. It's a nice little engineered water cycle there. Here's the thing. This treatment plant is not designed to treat water that has 5% biota. Right? Within the lake itself, water is going to dilute with the rest of the water such that that percentage can go down to 1%. And this treated water treats it starting at 1% and maybe releases it at 0.1% or something like that. Even there, as it travels through the pipe, you know that typically pipe system, has anybody ever lived next to a water treatment plant? If you do, your water will taste like chlorine, right? Because we pump water full of chlorine when it leaves the plant so that by the time it gets to the furthest house, it has no chlorine. But then all the houses in between will have chlorine. What? Ooh, good. Let's leave it here. On Thursday, we're going to talk about population growth. And yeah, I'll see you Thursday.